Welcome back to Bite-Sized Breakthroughs, the podcast where we break down cutting-edge research into digestible bits. Today, we're diving deep into a fascinating paper titled Evolutionary Optimization of Model Merging Recipes. Joining me is Dr. Paige Turner, a leading expert in large language model development, and Professor Wide Spectrum, a renowned scholar in the field of artificial intelligence. Dr. Turner, thank you for being here.
It's a pleasure to be here, Alex. I'm excited to discuss this groundbreaking work.
Professor Spectrum, always a delight to have you on the show. Your insights are invaluable.
Thank you, Alex. I'm eager to see how this research impacts the broader landscape of AI.
Let's start by setting the stage, Dr. Turner. Can you give our listeners a brief overview of the context surrounding this research? What's the problem the paper addresses, and why is it important?
Sure. The paper delves into the exciting world of model merging, a technique that combines multiple pre-trained large language models, LLMs, to create a single, unified model. This approach has gained significant traction because it's incredibly cost-effective. You don't need to train the model from scratch. You're essentially leveraging the existing knowledge of pre-trained models. Imagine you've got a bunch of experts, each with a specialized skill set. Model merging is about bringing those experts together to create a super expert capable of handling a wider range of tasks.
But there's a catch, right? This process isn't as simple as just stitching models together.
Exactly. The paper highlights that model merging often relies heavily on human intuition and domain knowledge. It's kind of like a black art. You need to have a good understanding of the models and their strengths to find effective combinations. This limitation restricts the potential of model merging, as it's not scalable and heavily depends on human expertise.
Professor Spectrum, can you elaborate on why this limitation is a significant concern for the field of AI?
It's a major hurdle in our pursuit of developing more powerful and versatile AI systems. We're constantly pushing the boundaries of what AI can achieve, and model merging holds incredible promise. But if we can't automate this process and make it more accessible, it'll remain a niche technique. This paper attempts to address that limitation, offering a more systematic and efficient approach to model merging.
So, Dr. Turner, what's the key innovation presented in this paper? What's the main solution they propose?
The authors introduce a novel method called Evolutionary Model Merge. Essentially, they're using evolutionary algorithms inspired by natural selection to automatically discover the best ways to combine different models. It's like letting a computer program breed new models by trying out different combinations and selecting the most successful ones. This approach is groundbreaking because it eliminates the need for human intuition and opens up a much wider search space for potential model combinations.
That's fascinating. But how exactly does this evolutionary approach work? Can you break down the methodology for our listeners?
Of course, evolutionary model merge operates by optimizing two orthogonal configuration spaces, the parameter space and the data flow space. Let's break them down. 1. Parameter space, PS. This space focuses on combining the weights of different models to create a unified model with the same architecture. It's like merging the knowledge of different experts by blending their skills. The authors utilize a technique called ties merging with DARE, which allows for granular, layer-wise merging. They use an evolutionary algorithm called CMAES to search for the optimal weights for each layer, maximizing the model's performance on a specific task. 2. Data flow space, DFS. Here, the emphasis is on optimizing the path that data takes through the model. The weights of each layer remain untouched. Instead, the algorithm determines the most effective sequence of layers from different models to process the input data. Think of it like arranging different specialists in a specific order to achieve the best outcome. They use a clever indicator array to manage which layers are included in the inference path and scaling parameters to adjust how the data flows between layers. Again, they use CMAES to search for the optimal configuration in this data flow space.
So they're optimizing both the weight combinations and the way data travels through the model.
Exactly, Alex. That's what makes this approach so powerful. It considers both aspects of model merging, leading to more effective and potentially surprising results.
Professor Spectrum, from a broader perspective, how does this approach compare to existing model merging methods? What are the key advantages?
Traditionally, model merging often involved simple weight averaging techniques. While effective, these methods typically relied on models fine tuned for similar tasks and often neglected the importance of optimizing the data flow. Evolutionary model merge introduces a significant shift. By automating the process and optimizing both parameter space and data flow space, it allows for the discovery of novel and counterintuitive model combinations that might not be easily identified by human experts. This leads to a much wider range of potential solutions, making it more likely to discover truly optimal models.
It seems like this approach opens up a whole new world of possibilities. Dr. Turner, what kind of experiments did the authors conduct to validate their method, and what were the key results?
They conducted two primary experiments. The first focused on creating a Japanese LLM capable of mathematical reasoning. They merged a Japanese LLM with two English math LLMs, and the results were impressive. Their merged model achieved an accuracy score of 55.2 on the MGSM-JA benchmark, which evaluates Japanese math problem solving. This score surpassed even some existing Japanese LLMs with significantly more parameters. For example, the Evo-LM-JP model outperformed Japanese stable LM70B, despite having only 10 billion parameters compared to 70 billion parameters in the other model. It also performed exceptionally well on the JP-LMEH benchmark, demonstrating its strong overall Japanese language proficiency.
That's a huge leap in performance. So, they essentially created a bilingual model that excels in both language understanding and mathematical reasoning.
Exactly. This demonstrates the power of evolutionary model merge to combine expertise from different domains. The second experiment aimed to develop a culturally aware Japanese vision language model, VLM. They merged a Japanese LLM with the LLM component of an existing VLM. Their Evo VLM JP model outperformed both the original VLM and a Japanese VLM trained from scratch on Japanese datasets, demonstrating its ability to handle culturally specific content.
This is truly groundbreaking. Professor Spectrum, what are the broader implications of these results? What does this mean for the future of AI?
This research presents a significant shift in how we approach foundation model development. It's a more efficient and potentially more affordable way to create powerful AI models. The ability to automatically discover effective model combinations could lead to the emergence of new and innovative AI systems with emergent capabilities. Imagine the possibilities: models that can seamlessly navigate different languages, cultures, and domains, ultimately pushing the boundaries of what AI can accomplish.
It's exciting to think about those possibilities. But Dr. Turner, are there any limitations to this approach that we need to consider? Are there any potential drawbacks?
Yes, there are limitations. While the method is very effective, it still inherits the limitations of the source models. The models produced by evolutionary model merge might still exhibit biases present in the source models, and it doesn't address issues like instruction fine-tuning or alignment, which are critical for ensuring factual accuracy and minimizing harmful biases. Additionally, the current study only focuses on two specific domains. We need more research to assess the method's effectiveness across a wider range of tasks and domains.
Professor Spectrum, how do you see these limitations impacting the adoption and application of this research in the real world?
These limitations are important considerations. We need to be cautious about relying solely on this approach without addressing these challenges. The field of AI is rapidly evolving, and we need robust methods to ensure the responsible development and deployment of these powerful technologies. However, the potential benefits of this research are significant, and with further investigation and development, it could revolutionize how we build AI systems.
Dr. Turner, what are some of the key future directions for this research?
The authors envision several exciting areas for future exploration. One is exploring the use of evolutionary algorithms to select candidate source models for merging, automating the entire process from start to finish. Another is investigating the creation of swarms of diverse foundation models, each with its own specialized capabilities, to form a collective intelligence capable of self-improvement. They also plan to extend the method to handle more complex data flow arrangements, leading to even more powerful and versatile models.
Professor Spectrum, How do you envision this research shaping the future of AI? What are some potential applications beyond what we've discussed so far?
This research has the potential to drive significant advancements in various fields. It could revolutionize natural language processing, making language models more powerful and capable of handling a wider range of tasks. It could also lead to breakthroughs in vision language understanding, enabling AI systems to interpret and understand visual information more effectively. Furthermore, this approach could be applied to develop more sophisticated AI systems for translation, summarization, question answering, and even code generation.
Dr. Turner, in conclusion, what are the main takeaways from this groundbreaking research?
This research showcases the transformative potential of using evolutionary algorithms to automatically discover and combine pre-trained models. Evolutionary Model Merge offers a more efficient and cost-effective way to develop foundation models, pushing the boundaries of what AI can achieve. By leveraging the knowledge of existing models and optimizing both parameter space and data flow space, this method unlocks a wider range of possibilities and enables the creation of powerful models with emergent capabilities. This research paves the way for a new era of AI, where AI systems are not just trained, but also evolve to tackle increasingly complex and diverse tasks.
That's a powerful message, Dr. Turner. Thank you for sharing your insights and expertise with our listeners. Professor Spectrum, your insights have been invaluable as always.
My pleasure, Alex. This research is truly fascinating, and I'm excited to see where it leads us in the future of AI.
And to our listeners, we encourage you to continue exploring this exciting field of AI research. Stay tuned for more insightful discussions on bite-sized breakthroughs.